All right, hi everybody. Roland Case here from the North Carolina Museum of Natural Sciences and North Carolina State University. And I'm here on the fourth and final installation of these tutorial videos about using the Snapshot USA analysis tool. And this is where it's going to get really interesting. In the past, we've been exploring patterns of detection rates, occupancy, activity patterns, and species diversity. And now we're going to be able to intersect some of those with environmental covariates. It means like what was going on the ground? What were the conditions where these cameras were run? And we can start to think about how those might affect the mammals that we're measuring. And we're using the Google Earth Engine for this. So Google Earth Engine collects these remote sensing data. A lot of these are originally collected by NASA or other spaceborne instruments that are measuring the environment. And now we're able to see how those affect. And so what I'm going to show you first is some of the variables that we have to work with. So you can see here, we're going to correlate species richness, occupancy, or detection rate. And then these are the covariates we have. So let's start with elevation, and we can display asset on map. And you can see there's the elevation profile of North America, right? And let's make it color because it's prettier. Okay, so we can automatically see that some of these dots, right, where we have camera trap arrays, some of them are in the mountains. And so they're going to have higher elevation, and some of them are in the lowlands. And so we'll automatically get that information. Not only elevation, also tree cover, right? What's the forest cover? Lots of variation in this. How does this affect mammals? You can now check it out for yourself. Net primary productivity. This is basically how much sort of plant production is available. Might be important for some herbivores. Human population density. So this is just the number of people, where the density of people. And then we also have this global human modification index, which is basically a combination of human population plus agriculture plus roads and trains and stuff like that. So it's kind of a combination. And if you zoom in, you kind of get a feel for what that's measuring. And so it's not just human population size, but some of the other things that we have, other factors that we have on the environment. What else? Precipitation, big gradients in this, especially east to west in the United States. Um, Temperature, and finally, topographic ruggedness. This is basically how bumpy is the landscape, right? Because, some of the West Coast is higher than the East Coast, but it's still pretty bumpy. It's still mountainous. So this is how much terrain there is basically at that site. Okay, so now you have an idea of what we've got to work with. And I'm going to start by looking at some species diversity. Now, what's interesting is species richness. Let's just hopefully you've got when you want to do this, first you need to add a group. Let's just go all mammals, all species everywhere, save group. How does this relate to? So this is the first thing I did. GPP, net NPP, net primary productivity, right? We think the more plants, the more mammals you should have. But look at this graph. It's not working out that way, right? So this is showing you net primary productivity down here at each camera array that we ran and how many species that camera array detected. And so you can see the R square is not high, right? If a perfect correlation would be 1, this is 0.01, and you can see it's a slight negative trend. So not what we were expecting at all, not the main driver. Now we know from our earlier exercise that species richness also depends on how many cameras you've run, how long you've been running your cameras for. So it might not be the perfect measure, but it's certainly one we can play with. We can test some hypotheses. You might want to try, instead of like everywhere, maybe a more narrow swath, like just in Texas or just in California or across a more local area of diversity. Or you could also, let's see, I'll show you this other filter. Let's just do the rodents. We'll do all the rodents. So do all rodents everywhere. Let's get rid of all species. let's see if we do any better with the rodents because they're herbivores, right? For the most part, rodents are all herbivores. Um, Not doing great. A little bit of a positive, but still, you can see the R squared is tiny. So not much going on here. But give it a try. See what you can find. We've got lots of species, lots of places, and lots of correlations to check out. Okay, so let's try something different. Instead of species richness, let's try occupancy. We're going to play around with occupancy and detection rate. So let's add a new group. Let's get rid of this family thing. Um, and then let's just try white-tailed deer. Okay. We know they tend to do well near people. So let's try, white-tailed deer everywhere. Save group, right? So now that's here. Now we can start playing around with these things. Let's try global human modification index. That's what that looks like. You can turn that off if you find that distracting. But let's go ahead and make the graph. So this is kind of interesting. Occupancy, right? 0 to 100. A lot of times deer are at every single camera trap. And there's a slight trend for that to increase where there's more people, but it's not a very high R squared. So interesting, not a whole lot of relationship here. But occupancy, again, it's stuck at 100. Where, we need another measure. And so if we change this to detection rate, now we get more of a significant relationship, showing that where the global human modification index is higher, that means more human disturbance, you generally get more deer activity, more deer on the camera, R squared of 0.1. So it's explaining about 10% of the variation in this, which isn't bad for just a bivariate correlation. Um, so this is something I'm sure you guys are going to want to try with different species, maybe even a subset of, how does it work just in North Carolina or just in Michigan? Will be super interesting to see that. Definitely check out, well, let's check out squirrels real quick. Um, so add a new group. Let's go, I'm going to turn off and then say Eastern gray squirrel. Everywhere, save group. Now this time, instead of human modification, let's look at human population density because we do this slightly differently. And so I'm going to make sure we talk about it for a second. We'll do detection. We'll do occupancy. You should try them both. But so one of the things that we've done here with human detection, with human population, is we've done this on the log scale because it's not a normally distributed variable. There's lots of very, very, very low values. And so this is a linear correlation, but it looks funny because of the log scale down here. So 0.05, somewhat of a positive that it goes up at higher numbers. Let's go ahead and try detection rate. Might look better, might not. I can't remember. Yeah, yeah, there you can see it's really going up at the higher abundances with wow, some really crazy one up there at 12 detections per day. That's a lot of squirrels. Wow, I have to figure out which place that is. So definitely a positive, and now you understand how this human population um, works with the log scale. Um, So we can check out some other ones. Let's check out, just for fun, let's try raccoon, another raccoon, uh, everywhere. And this is, we can just fly through. Well, how do they deal with temperature? Generate graphs. Okay. Somewhat of a positive, but not too great. And we can just jump, quickly to precipitation. Not much there. Um, how about elevation? Okay. This is interesting. They decline. Um, so if you look at where there are a lot of raccoons, it's low elevation. And where they occur at high elevation, they're definitely at lower abundances. Um, I wonder about raccoons and human population. You should check it out. Okay, the last thing I want to show you is how this is useful for looking at niche dimensions of a species, right? What's a niche dimension? Well, the niche is like what conditions are a species adapted to survive in. We think about things like temperature and rainfall and really all of these, elevation. Um, there's conditions that species are adapted to, and they might be different for different species. Um, so as one fun example, um, let's let's look at the cottontails. Okay, we've got different cottontail rabbits. Let's try desert cottontail everywhere. And then let's try um, eastern cottontail everywhere. Save group, right? Um, and let's look at, right, you think about desert, right? So this isn't too surprising. Desert cottontail, maybe there's a rainfall difference. So let's generate these graphs. You can see the rainfall gradient across the United States, right? Lots of rain in the east, southwest, not much rain. Now, if we look at this graph, look at this. This is really cool. This is the detection rate. You can kind of ignore these lines for now. They both have a negative trend, but just look at the distribution. Eastern cottontail, red dots, only in the wet, in the more wet areas, um, and the desert cottontail in the more dry areas, and right around 500 millimeters is where that shifts off, right? Very few desert cottontails greater, and very few eastern cottontails colder, drier. Um, it's also, I think, interesting to look at the shape of this relationship, right? That a lot of times species in their niche dimensions, um, and let's try this. Let's because it's easy enough. Let's just look at only um, only the eastern cottontail. But here's something that might be useful. If we add, let's just add a group that's all species. Um, and this is just going to show us the full range of values that we have cameras at. So this is everywhere. So the blue is showing, you can ignore the blue on the detections per day, but it shows you that we had cameras down here and we didn't detect eastern cottontails. And we had cameras up here, and we did get them once here, but a couple places we didn't. So the range of variation that eastern cottontails can survive is somewhere, well, there's one here, but somewhere between 1,700 and 1,500. But they're most common seems to be in the kind of mid-range, around 1,000, um, and a little bit drier. And here, where it gets really wet, well, they can survive, but nowhere are they super abundant. So anyway, kind of an interesting way to look at the niche dimensions of an animal by annotating the data. So I hope I've given you guys some stuff to chew on, some seeds for ideas. There's so many species, so many sites, so many different metrics, environmental correlations, lots of questions that we don't know the answers to. And you guys are going to be able to mine out of this data set some interesting things that your professors don't know, that I don't know, that's not published in the scientific literature, and I can't wait to see what you find.